I briefly introduced tries last time already, and I won't get into the discussion of where the name comes from again this time. But I want to discuss the second part now a bit more detail. So you should think of tries as trees where a node has as many children as there are symbols in the alphabet. So we often want to use these for restricted alphabets. Like in this case, the alphabet is binary. It's just the letters A and B. Now I realize that there's also this dollar symbol, and we'll talk about that in a second. But first of all, a node can have two children, one for each letter in the alphabet. It can also have just a single child as this one. And so the idea in a trie always is if you follow a path from the root down the tree, like the one I sketched here, and you read the letters that you find on this path, then they give a string. And if that path leads to a leaf, then this leaf should contain exactly that string. So if you want to search for a string, say we search for, we want to know whether ABA is contained in this trie. We would start at the root. The first letter is an A, so we go with the A branch. Then we look at the second letter, which is a B, so we would go the B branch. Then we find an A, so we would go the A branch. And at this point, we would like to see this dollar symbol, but there's no edge with a dollar symbol. So here we fall out of the tree, and we can report that this string does not occur in the dictionary that is represented by the trie. Otherwise, there would have been an edge with that label. So this is what I tried to draw here. This was a little lightning bolt symbol, meaning that we are kind of stuck. But really what it just means, it's not in the symbol table. It's not contained in the set of strings stored represented by this trie. Now, if you look at this, just this alphabet AB, if there were no dollar symbols, then we could have had this string ABA that stops in the middle of this internal node. And for various reasons, that's kind of a nuisance and inconvenient. So we will usually make this assumption for tries that the strings that we store, this set of strings, is prefix free. So what that means is no string is a strict prefix of any other string. And then you never have this situation that you have to stop in the middle of a tree. And there's two simple sufficient conditions, each of which guarantees the prefix freeness. And you can have either of the two. It depends which is convenient. If the strings are all of the same length, well, if they're the same length, neither can be a prefix of another, a strict prefix. So by strict prefix, I mean it's a prefix and it's not the same string. Duplicates are not really allowed here anyways. So if all the strings are the same length, they're prefix free. Another option, in general, if you have any set of strings, you can make it prefix free by appending an end of string character. And we'll always use this dollar symbol because it somehow became customary. Don't ask me why. At the end, everything comes down to dollars. But the only real significance is it is some symbol that doesn't occur in the alphabet. And it's convenient to have something you can type quickly. So I guess that might be the reason. And so in this case, the set of strings might originally have been AA and AAAB and ABAAB. It's tough to pronounce. And then we append this dollar symbol, and then it became prefix free. Whereas previously, right, this AAA would have been a prefix of AAAB. All right. What else can we do with tries? We can insert a new symbol into the set. I thought it might be helpful to do this once on this example because many of you have never seen tries. So let's pick a string that's not already in the set. How about we do something short? BB dollar is not yet in the set. So let's try to insert this. What we do for that is we start at the root, and now we try to search for this string, which is a natural thing to check. Is it already in the dictionary? In which case we would not have to do anything. We know it's not in this case, but we still do the search. So we follow this path because the first letter of BB dollar is a B. So let's give this a name. Let's call this S. Then I can say this was the first character in S, so the character at index 0. Then I reach this node, there's another character, so I can follow this link, which is the character at index 1. And now the original string was finished here, but we added this $sign. So I want to add another, I want to follow another edge with a $sign. Now in this case, there is no such edge. But that's good because we wanted to insert. So we kind of want or expect that there is a missing edge at some stage. And so I'm just making a new one and then add the string as a new leaf. Okay. And that happened to be the second character at index 2. That's how you insert in a try. You try to follow the path as long as that works, and as soon as it stops working, you add new nodes and edges until you have inserted the new string. This could have gone on for longer. It could have been necessary to add more nodes, and then you would have created such unary paths of, we always have just one character for each edge, so we might add many more vertices. Deletion is also simple. If I wanted to delete, say, a dollar, I would start at the root. I follow a dollar. Here it is. I found it. And so deletion would just remove this and all the unary nodes above it. In this case, it's just a single edge. If we had deleted this one, we would have removed these three nodes. So the leaf and all the nodes with just a single child above it. So that's pretty much what tries can do. And next I want to see if you digested this. It's a long question, so you might need a second to read this. So the first thing to note is all strings are same size, same length. And let's say search means, is this query string contained in the set represented by the try or not? That's the simplest query, I guess. Okay, 20-ish, we're reaching number of people in the room, but there's a few at home maybe. Well, at least 3. We had 40 votes for the other question that was open for a couple of days. But I don't want to wait a couple of days. Someone pointed out that for some of the questions, I stopped them a little early. And because I'm giving you points for participation, that's kind of mean. So I try not to do it. But I also try not to show you the votes and influence in your decision to vote. So I'm not sure what to do. I could either just wait a little longer, which may be the easiest solution, but I'm such an impatient person. Or I could show you the results, and the danger is some of you might just change their mind or vote after you've seen the results. I think the second option is better, given that I'm such an impatient person. So I'll just leave the polls open so you can still vote. But yeah, you're cheating on yourself if you wait for that. It's quite interesting that there. So first of all, I was mean again. I put in a lot of different options because I thought I'll throw in anything you could potentially come up with, misguided as you might be initially, maybe. So there's lots of different options, but you see some peaks, but nothing really decisive. It's really interesting. All right, so let's discuss this a bit. I'll show you the answer here. The one that I have in mind is this one, theta of q, so roughly as long as the query string is. I think it's easiest to illustrate on the example again. So what we do with a query string is we traverse down a path. So remember, we use this red example here. Okay, trouble with my pen again. We use this red example to walk down the tree, and after 4 steps, which happens to be the number of characters in the query, so q, we noticed, oh, we fell off the path. If we're lucky, we fall off the path already earlier. If we notice, say we're looking for just $1, no A's and B's in front, then right at the root we would notice there is nothing. A slightly more interesting example could be, it's a fairly full tree, but maybe something that starts with BA and then goes on for millions of characters. I would still notice after the first B and then an A isn't in the try, so I can stop early. So I can sometimes decide that something's not in the try early. To decide that it is in the try, I always have to follow the entire pattern down until I reach the leaf. And so that's what's meant in this case. I should probably narrow it down and say a successful search, because theta of q is an upper and a lower bound. And I just convinced you that if the pattern is not in the try, you might actually stop after just 1 or 2 characters. On the other hand, we can argue this is the worst case over the data. So okay, there's a lot of slack in how you interpret the question precisely. But the usual way is you traverse down the try, and how many steps do you go down? As many as the query string is long. Okay? Now I want to take a step back here and say why this is so cool and exciting. Because the try could be really humongous. This could be an index over a huge collection of texts. Think of a search engine for the entire web. But the time to query for whether something occurs in this huge collection only depends on the length of what you query. So if you look for, you're trying to find a username and you want to see if that's unique, if no one came up with blah, 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 then you just type that in, and in the length of that string time, you know whether someone has already used that on any of the websites that there are, the trillions of websites. I think that's quite remarkable, even though there are some strings attached to it. And that brings me to this second question. So a similar setup. Again, n strings, each m characters over, say, the Latin alphabet. And now the question is, how many nodes could a trie have in this situation? And by nodes, I mean the little red dots, right, from the picture. And worst case is important. So how many people did we really have last question? 22. No, that's now really 44. Amazing, guys. Where do you all hide? Okay, 33. Okay, almost there, but I guess I'll just not lock the question so I can show you the results. It's a little more telling this time. Seems to be a clear peak. And this is also the correct answer. So why is it n times m? It is a little tricky, but that is effectively the worst case. What you should think about for the worst case is you branch out as early as possible in the strings, so they have all a unique prefix, and then they continue as these unary node chains. So how would this look like roughly? There's our root nodes, and we have some 26-ary tree. It's not a binary tree, it's a node where every node, a tree where every node has 26 children, the letters of the alphabet. And you keep doing this for a certain number of levels. Well, how many? Essentially log n levels. Oh yeah, I didn't change the screen. Thanks. And now that screen went off again. So here's my schematic picture. You have a node, then you have log n levels deep. Then you branch out to n nodes at this level, and then you go in long chains until you reach the leaves at each point. And so you have this n minus log n levels that you still go down. These are all binary, all unary nodes. So you have this m times, sorry, that's m minus log n. And each of these chains is, so you have n chains, and each of these chains has length m minus log n. And so you multiply out, the dominant term is n times m. Okay. So that's only the unary nodes in this second half of this long jellyfish or whatever, the tentacles. Okay, so again, step back from this example. Is that good or is that bad? It's terrible because that's a lot. That's a lot of space. It's a lot of nodes. And if the alphabet is big, each of these nodes has to somehow at least allow to store all these children it could have. Whereas most of these nodes, they only have a single child. So it's a huge waste of memory. If you say every node is represented with an array of 26 possible child links, then that's 26 times the length of all the strings together. So that's a huge overhead for storing this structure. So I don't I don't think Google wants to store an index that's 26 times the size of the internet. And that's not even taking all characters into account. Remember, Unicode was more like 150,000 characters. So that's kind of a no-no. So tries have this big problem that they're space inefficient. And at least in a way here, this seems inevitable in the tree structure. Like if you have to store these strings that differ in the first few characters and then go on whatever for a long time, you have to somehow store them. So it seems you can't avoid this with this kind of tree structure. But there's a way out by modifying the data structure. And that's what people call compact tries. The bad thing in the worst case example I've shown you was that you have these long tentacles of unary nodes. What if we avoid those altogether? So whenever we have a unary node, like in this case, we remove that node and make it into one long edge. So this unary node was gone, it's consumed into one edge, and it became this edge. Okay? And you can do this further down. So here as well, long unary chain became just one edge, this one. Now, there's a few things we have to talk about. First of all, does this help? Second, how can we still search? And part of the second is, what do we write on the edges? Here we have only space for a single character, but I have BB on the path down that I contracted. And so the rule is we just use the first of these characters and we forget about the rest. They're not really forgotten because they're still stored in this leaf, so we can recover. But we have to pay attention now if we follow down a path that we compare the right characters. And that's why the compact try additionally stores these numbers in the nodes. They tell you what index you're looking at next. So at the root, there's a 0, which means you first compare the 0 position, the 0 index of the string. And if that's a B, you go that way. Now, the next node says 2, which means you ignore what's at position 1, and you start immediately with position 2. So what that means for a search, if you were to search for BAB$, it means you start here. 0th character here is a B, so you go down here. Second character is a B, so you go down here. And so you found a leaf, and you say, yeah, the word appears. But not so fast this time. You still have to compare the string that you're searching to what you find in the leaf, because we skipped this middle character, and in general, we can skip many characters. So you still have to, at some point, check those. That's why we still keep the strings in the leaves, but the search can take shortcuts. Now back to the second point, did this help? What we achieved by removing all unary nodes is that every node that remains in the compact try has at least 2 children. And that helps a lot because it means we never have more nodes than there are leaves. That's the same argument that we've used for binary tree counting before. Whenever you add a new binary node, or whenever you add a new node that has at least 2 children, it adds at least 1 more leaf, because it branches into 2, so you can plug it into some path. So it might take 1 leaf that was previously there and take it in one side, but then it has another side, so you have to create a new leaf whenever you add an internal node. So if you invert that argument, the number of nodes is at most the number of leaves minus 1. And that's the number of strings. So now the number of nodes is order n now, where n is the number of strings, and not n times m. Okay? We still store the strings in the leaves, so we still need this n times m space, but the constant factor is much better because the number of nodes is smaller. We just store the strings. We don't store something 20 times as big, 26 times as big. So we'll usually work with compact tries because they're much more space efficient and usually also faster, even though they're a little more complicated to do the searches. And that brings me to the end of this first part. If you want an inverted index, you can use a try to implement that and get very efficient searches. It's relatively simple, at least conceptual. You need to implement a try. There's tricky parts inside. How do you represent the nodes? You have basically two options. You can say every node stores the space for all possible child links. That is a little waste in space, but it's fast. Another option could be each node stores a little dictionary of a symbol table of child links that uses less space, but then you need the time inside the symbol table to search for the child link given a character. So that's a little more space efficient, but slightly slower. And there's nice trade-offs there. But it's overall a relatively conceptually simple data structure still. And lookup is almost as fast as it can get. You just need the time to read the pattern. But there are some downsides, and these are not really restricted to tries, but to inverted indices in general. What if you're searching for just a part of a word and you haven't spelled it out? Might be less of a problem in English, but languages like German, where you can create compound nouns that can grow arbitrarily long. If you haven't seen that, there's a nice YouTube video. Maybe I'll post this. It's probably a little tough to follow unless you speak German. But the thing is, you can make words arbitrarily long, and you can essentially tell a story in one single word. If your inverted index contains that word, that's great, but you can't search for parts of the word. And the other restriction is if you want to search something slightly more complicated, not just a single word, but a sequence, there's no easy way to do this efficiently in the try. You need to store extra things for that. And then the second bigger disadvantage, what if there's no words to start with? If you have just some binary string that you would like to search for patterns, there's no way to build an inverted index. And similarly for these biological sequences, DNA or RNA sequences, the genome of the coronavirus, all these things, there's no word boundaries. So it seems like this doesn't work well for this.